Okay, so this is part 23, and yeah, I lost my streak. Holy crap. I was busy the last few days with work, so hopefully I could finish all of this today. The whole pre-algebra 96%. Finish the exponents, values, interpolations, and then start the course challenge. Am I recording? I am recording. Oh gosh, where was I? The last thing I did was... Okay. Negative exponents.
We already know that 2 to the 4th power can be viewed as starting with a 1 and then multiplying it by 2 4
Just a second.
or it can be viewed as starting with a 1 and then multiplying it by 2 4 times. So let me do that. So times 2 times 2 times 2 times 2, and that will give us, let's see, 2 times 2 is 4, 8, 16. So that will give us 16. Now I will ask you a more interesting question. What do you think 2 to the negative 4 powers? I encourage you to pause the video and think about that.
It's like,
You might be tempted to say, oh, maybe it's negative 16 or something like that. But remember what the exponent operation is trying to do. This is one way of viewing it. This is telling us how many times are we going to multiply 2 times negative 1. But here we're going to multiply negative 4 times. What does negative traditionally mean? Negative traditionally means the opposite. So here this is how many times you're going to multiply. Maybe when we make it negative, this says how many times we're going to start with a 1. How many times are we going to divide by 2? So let's think about that a little bit. So this could be viewed as 1 times, and we're going to divide by 2 4 times. Well, dividing by 2 is the same thing as multiplying by 1/2. So we could say that this is 1 times 1/2 times, just do one color. So 1 times 1/2 times 1/2 times 1/2 times 1/2. Notice, multiplying by 1/2 4 times is the exact same thing as dividing by 2 4 times. And in this situation, this would get you 1/2, well 1 times 1/2 is just 1/2, times 1/2 is 1/4, times 1/2 is 1/8, times 1/2 is 1 over 16. And so you probably see the relationship here. If this is essentially, if you're starting with the 1 and you're dividing by 2 4 times, you could also say that 2, I'm going to do the same colors, 2 to the negative 4, 2 to the negative 4 is the same thing as 1 over 2 to the 4th power. 1 over 2 to the 4th power. Let me color code it nicely so you realize what the negative is doing. So this negative right over here, we'll do it in a better color, I'll do magenta, something that jumps out. So this negative right over here, this is what's causing us to go 1 over. So 2 to the negative 4 is the same thing, based on the way we've defined it just up right here, as 1 over is the reciprocal of 2 to the 4th, or 1 over 2 to the 4th. And so you could view this as being 1 over 2 times. So 2 times 2 times 2 times 2. If you just do 2 to the 4th as taking 4 2's and multiplying them. Or if you use this idea right over here, you could view it as starting with the 1 and multiplying it by 2 4 times. Either way, you are going to get 1 over 16. 1 over 16. So let's do a few more examples of this just so that we make sure things are clear to us. So let's try 3 to the negative 3rd power. So remember, whenever you see that negative, what my brain always does is I'm going to take the reciprocal here. So this is going to be equal to, I'm going to highlight the negative again. This is going to be 1 over 3 to the 3rd power. 1 over 3 to the 3rd power, which would be equal to, well, 1 over 3 times 3, or you could say 1 over 3 times 3 times 3, or 1 times 3 times 3 times 3 is going to be 27. So this is going to be 127. Let's try another example. I'll do 2 or 3 more. So let's take a negative number to a negative exponent, just to see if we can confuse ourselves. So let's take the number negative 4 -4. And let's take it. I don't want my numbers to get too big too fast. So let's just take -2. Let's take -2. And let's take it to the -3 power. Negative, I'm going to make my negative magenta. -3 power. -3 power. So at first this might be daunting, the negatives cancel, that'll just be the remnants in your brain that are trying to think of multiplying negatives. Do not apply that here. Remember, you see a negative exponent, that just means the reciprocal of the positive exponent. So 1 over -2, -2 to the third power, to the positive third power, and this is equal to 1 over -2 times -2 times -2 times -2, or you could use 1 times -2 times -2 times -2, which is going to give you 1 over -8 or negative -1/8. Just start squinching things. So this is equal to -1/8. Let's do one more example, just in an attempt to confuse ourselves. Let's take, I don't know, let's take 5/8 and raise this to the -2 power. -2 power. So once again, it's negative. I got a fraction, it's negative here. Remember, this just means 1 over 5/8 to the second power. So this is just going to be the same thing as 1 over 5/8. 1 over 5/8 squared. 1 over 5/8 squared, which is going to be the same thing. So this is going to be equal to, trying to color code it, 1 over 5/8 times 5/8, which is 25 over 60. 25 over 64. 1 over 25 over 64 is just going to be 64 over 25. So another way to think about it is, you're going to take the reciprocal of this and raise it to the positive exponent. So another way you could have thought about this, is 5/8 to the -2 power. Let me just take the reciprocal of this, 8/5, and raise it to the positive 2 power. So all of these statements are equivalent. And that would apply even when you are dealing with non-fractions as your base right over here. So 2, you can say, well, this is going to be the same thing. 2 to the -4 is going to be the same thing as taking my reciprocal. So this is going to be the same thing as taking the reciprocal of 2, which is 1 over 2, and raising it to the positive 4 power.
Wow.
Of 2 to the positive, which is 1 over 2, and raising it to the positive 4.
Let's see what's easier. Okay. It seems pretty much more straightforward than this.
I have been asked for some intuition as to why, let's say, a to the minus b is equal to 1 over a to the b. And before I give you the intuition, I want you to just realize this really is the definition. I don't know, the inventor of mathematics, wasn't one person, it was, a convention that arose. But they defined this, and they defined this for the reasons that I'm going to show you. Well, what I'm going to show you is one. For the reasons that I'm going to show you. Well, what I'm going to show you is one of the reasons, and we'll see that this is a good definition because once you learn the exponent rules, all the other exponent rules stay consistent for negative exponents and you raise something to the 0th power. So let's take the positive exponents. Those are pretty intuitive, I think. So the positive exponents, so you have a to the 1, a squared, a cubed, a to the 4th. What's a to the 1? A to the 1 we said was a. And then to get to a squared, what did we do? We multiplied by a, right? A squared is just a times a. And then to get to a cubed, what did we do? We multiplied by a again. And then to get to a to the 4th, what did we do? We multiply by a again. Or the other way you could imagine is when you decrease the exponent, what are we doing? We are multiplying by 1 over a, or dividing by a. And similarly, decrease again, you're dividing by a. And go from a squared to a to the 1st, you're dividing by a. So let's use this progression to figure out what a to the 0 is. So this is the first hard one. So a to the 0. So you're the inventor, the founding mother of mathematics, and you need to define what a to the 0 is. Maybe it's 17, maybe it's maybe it's pi. I don't know. It's up to you to decide what a to the 0 is. But wouldn't it be nice if a to the 0 retains this pattern? Every time you decrease the exponent, you're dividing by a, right? So if you're going from a to the 1st to a to the 0, wouldn't it be nice if we just divided by a? So let's do that. So if we go from a to the 1st, which is just a, and divide by a, right? So we're just going to divide by a. What is a divided by a? It's just 1. So that's the definition, or that's one of the intuitions behind why something to the 0th power is equal to 1. Because when you take that number and you divide it by itself one more time, you just get 1. So that's pretty reasonable, but now let's go into the negative domain. So what should a to the negative 1 equal?
Keep going dividing by 8.
Well, once again, it's nice if we can retain this pattern where every time we decrease the exponent, we're dividing by a. So let's divide by a again. So 1 over a. So we're going to take a to the 0 and divide it by a. A to the 0 divided by a. A to the 0 is 1. So what's 1 divided by a? It's 1 over a. And let's do it one more time, and then I think we're going to get the pattern. Well, I think you probably already got the pattern. What's a to the minus 2? Well, we want, it'd be silly now to change this pattern. Every time we decrease the exponent, we're dividing by a. So to go from a to the minus 1 to a to the minus 2, let's just divide by a again. And what do we get? We get, if you take 1 over a and divide by a, you get 1 over a squared. And you can just keep doing this pattern all the way to the left, and you get a to the minus b is equal to 1 over a to the b. Hopefully that gave you a little intuition as to why. Well, first of all, the big mystery is, well, something to the 0th power, why does that equal 1? First, keep in mind that that's just a definition. Someone decided that it should be equal 1, but they had a good reason. And the good reason was they wanted to keep this pattern going. And that's the same reason why they defined negative exponents in this way. And what's extra cool about it is not only does it retain this pattern when you decrease exponents, you're dividing by a, or when you're increasing exponents, you're multiplying by a, but as you'll see in the exponent rules videos, all of the exponent rules hold. All of the exponent rules are consistent with this definition of something to the 0th power and this definition of something to the negative power. Hopefully that didn't confuse you and gave you a little bit of intuition and demystified something that frankly is quite mystifying the first time you learn it.
Yeah, fair enough. Oops. Wow. Real expression for 7 over 3 over 7. Where's the positive? Oh wow, oh, makes sense. Justification number patterns.
Let's get some practice with our exponent properties, especially when we have integer exponents. So let's think about what 4 to the negative 3 times 4 to the 5th power is going to be equal to. And I encourage you to pause the video and think about it on your own. Well, there's a couple of ways to do this. One, you say, look, I'm multiplying two things that have the same base. So this is going to be that base, 4, and then I add the exponents, 4 to the negative 3 plus 5 power, which is equal to 4 to the second power. And that's just a straightforward exponent property, but you can also think about why does that actually make sense. 4 to the negative 3 power, that is 1 over 4 to the third power. Or you could do that as 1 over 4 times 4 times 4, and then 4 to the 5th. That's 5 4s being multiplied together. So it's times 4 times 4 times 4 times 4 times 4. And so notice, when you multiply this out, you're going to have 5 4s in the numerator and 3 4s in the denominator. And so 3 of these in the denominator cancel out with 3 of these in the numerator.
4 over.
So you're going to be left with 5 minus 3, or negative 3 plus 5 4s. So this 4 times 4 is the same thing as 4 squared. Now let's do one with variables. So let's say that you have a to the negative 4th power times a to the, let's say, a squared. What is that going to be? Well, once again, you have the same base. In this case, it's a. And so since I'm multiplying them, you can just add the exponents. So it's going to be a to the negative 4 plus 2 power, which is equal to a to the negative 2 power. And once again, it should make sense. This right over here, that is 1 over a times a times a times a. And then this is times a times a. So that cancels with that cancels with that, and you're still left with 1 over a times a, which is the same thing as a to the negative 2 power. Now let's do it with some quotients. So what if I were to ask you, what is 12 to the negative 7 divided by 12 to the negative 5 power? Well, when you're dividing, you subtract exponents if you have the same base. So this is going to be equal to 12 to the negative 7 minus negative 5 power. You're subtracting the bottom exponent. And so this is going to be equal to 12 to the, subtracting a negative is the same thing as adding a positive, a 12 to the negative 2 power. And once again, we just have to think about, why does this actually make sense? Well, you can actually rewrite this. 12 to the negative 7 divided by 12 to the negative 5, that's the same thing as 12 to the negative 7 times 12 to the 5th power. If we take the reciprocal of, this right over here, you would make the exponent positive. And then you get exactly what we were doing in those previous examples with products. And so let's just do one more with variables for good measure. Let's say I have x to the negative 20th power divided by x to the 5th power. Well, once again, we have the same base, and we're taking a quotient. So this is going to be x to the negative 20 minus 5. We have this one right over here in the denominator. So this is going to be equal to x to the negative 25th power. And once again, you could view our original expression as to the negative 25th right over here in the denominator. So this is going to be equal to x to the negative 25th power. And once again, you could view our original expression as x to the negative 20th, and having an x to the 5th in the denominator dividing by x to the 5th is the same thing as multiplying by x to the negative 5. And so here, you just add the exponents, and once again, you get x to the negative 25th power.
I've been recording.
Do some example raising exponents or products of exponents to various powers, especially when we're dealing with integer exponents. So let's say we have 3 to the negative 8 times 7 to the third, and we want to raise that to the negative 2 power. And I want you to pause this video and see if you can simplify this on your own. So the key realization here, there's a couple of ways that you can tackle it, but the key thing to realize is if you have the product of two things and then you're raising that to some type of a exponent, that is going to be the same thing as raising each of these things to that exponent and then taking the product. So this is going to be the same thing as 3 to the negative 8 and then that to the negative 2 times 7 to the third to the negative 2. So it'll be 7 to the third right over here. And if I want to simplify this, 3 to the negative 8 to the negative 2, we have the other exponent property, that if you're raising to an exponent and then raising that whole thing to another exponent, then you can just multiply the exponents. So this is going to be 3 to the negative 8 times negative 2 power. Well, negative 8 times negative 2 is positive 16. So this is going to be 3 to the 16th power right there. And then this part right over here, 7 to the third to the negative 2, that's going to be 7 to the 3 times negative 2, which is 7 to the negative 6th power. So that is 7 to the negative 6. And this would be about as much as you could simplify it. You could rewrite it different ways. 7 to the negative 6 is the same thing as 1 over 7 to the 6. So you could write it like 3 to the 16, use that same shade of blue. 3 to the 16 over 7 to the 6. But these two are equivalent. And there's other ways that you could have tackled this. You could have said that this original thing right over here, this is the same thing as 3 to the negative 8 is the same thing as 1 over 3 to the 8th. So you could have said this is the same thing as 7 to the third over 3 to the 8th, and then you're raising that to the negative 2, in which case you raise this numerator to the negative 2 and the denominator to the negative 2, but you would have gotten to the exact same place. Let's do another one of these. So let's say that we have got a to the negative 2 times I've got that it would say let's say that it would be as 3 to the negative 8 is the same thing as 1 over 3 to the 8th. So you could have said this is the same thing as 7 to the third over 3 to the 8th. And then you're raising that to the negative 2, in which case you raise this numerator to the negative 2 and the denominator to the negative 2.
Then you could reverse it.
You could have gotten to the exact same place.
If I make it positive, then we have 3 at the top. Oh wow, cool.
Let's do another one of these.
It's insanely cool.
So let's say that we have got a to the negative 2 times 8 to the 7th power. We want to raise all of that to the 2nd power. Well, like before, I can raise each of these things to the 2nd power. So this is the same thing as a to the negative 2 to the 2nd power times this thing to the 2nd power. 8 to the 7th to the second power. And then here, negative 2 times 2 is negative 4. So that's a to the negative 4 times 8 to the 7 times 2 is 14. 8 to the 14th power. In other videos, we go into more depth about why this should hopefully make intuitive sense. Here you have 8 to the 7th times 8 to the 7th. Well, you would then add the two exponents, and you get to 8 to the 14th. So however many times you have 8 to the 7th, you would just keep adding exponents, or you would multiply by 7 that many times. Hopefully that didn't sound too confusing. But the general idea is if you raise something to an exponent and then another exponent, you can multiply those exponents. Let's do one more example where we are dealing with quotients, which that first example could have even been perceived as. So let's say we have 2 to the negative 10 divided.
And this A over written as 8/14 over A4.
By 4 squared. And we're going to raise all of that to the 7th power. Well, this is equivalent to 2 to the negative 10 raised to the 7th power over 4 squared raised to the 7th power. So if you have the difference of two things and you're raising it to some power, that's the same thing as the numerator raised to that power divided by the denominator raised to that power. Well, what's our numerator going to be? Well, we've done this drill before. It would be 2 to the negative 10 times 7th power. So this would be equal to 2 to the negative 70th power. And then in the denominator, 4 to the second power. Then that raised to the 7th power. Well, 2 times 7 is 14. So that's going to be 4 to the 17th, 4 to the 17th power. Now, we actually could think about simplifying this even more. There's multiple ways that you could rewrite this. But one thing you could do is say, hey, look, 4 is a power of 2. So you could rewrite this as, this is equal to 2 to the negative 70th power over, instead of writing 4 to the 17th power.
Wow.
Why did I write 17th power? It should be 4 to the 14th power. Correct that. Instead of writing 4 to the 14th power, I instead could write, so this is 2, get the colors right. This is 2 to the negative 70th over, instead of writing 4, I could write 2 squared to the 14th power. 4 is the same thing as 2 squared.
Wow.
And so now I can rewrite this whole thing as 2 to the negative 70th power over, well, 2 to the second, and then back to the 14th. Well, that's 2 to the 28th power. 2 to the 28th power. And so can I simplify this even more?
Yeah.
Well, this is going to be equal to 2 to the, I can just, if I'm taking a quotient with the same base, I can subtract the exponent. So it's going to be negative 70.
98.
It's going to be negative 70 minus 28th power. Minus 28. And so this is going to simplify. 2 to the negative 98th power. And that's another way of viewing the same expression.
Activities now. Equivalent expression. 1 over y positive 2. Why is there a function here? It's very select expression. 7 z raised to negative 20. 1 raised to 2 raised to 4. 1 over 2 raised to 4. So this is 6 to the negative 5th power. Write the expression in the form. Okay. Wait, what? Raised to, oh my god, what is this? Positive 5? A raised to negative 19 No. -7. Okay, what's this? 8 raised to -5. 5 raised to -13. The expression in the form z raised to n. Z raised to -26, I believe. Y raised to 6. 5 raised to 18. Okay, cool. Powers of products and quotients, integer exponents. Okay, sure. Select the equivalent expression. Oh wow, this is insane. Let's see. This is x -3. I don't have enough room to write my shit. Okay, let's see. -3, -7 multiplied by y 7, which equals to x raised to 21 times x raised to 21. Not really x, it's actually y. Wow, holy shit. It's like -21. What's for this? No, that can't be. Can't do this because they're given different place. Oh man, it's literally what I did. Okay, select the equivalent expression. This is e raised to 12 over y raised to -10. I guess it's complicated. Multiply the constant. Yeah, because that is literally equivalent. 3 over 12 times 1 over y positive 10. Or multiply that, we're reciprocal of that 1 y then positive. Select the equivalent expression. That's going to be 8 raised to 20, and we have 2 raised to positive 8. Oh wow, this is actually it. I guess just one answer. This is 6 raised to positive 36 multiplied 8 over 7. 63 actually. Integer exponents. Okay, cool. Okay, so this is like subtracting a negative, so we have 4 raised to -2. Choose two answers, okay. 4 raised to negative 2 or b over 1. B are 1 over 4 raised to 2 and no, it's actually this one. Let's see. This is 4 raised to negative. Is this raising the ship? Oh no. Let's actually solve this. So 4 to negative 3 times 4. It should be this one. Oh, you're already wrong with your first mistake. Or it's a step wrong. No way, man. So you can do that? Oh, PEMDAS, parenthesis, okay. Then why in the video we did the exponent first? The 4/5 negative 3. And look, oh my god. Okay, which expressions are equivalent to 7 negative 2? I'll choose to answer. So this is the same as 7 raised to positive 4. This is the same shit. Let's see other. This is required. Not sure. It could be. It's in any order, it says. Wow, okay. It's not clear. It's this one? Or this one? No way, it's this one. Okay, I'm pretty sure this one's not correct. So how is this correct? What the fuck? What the fuck? Shit. Yo, what the fuck is this? Oh, is this correct? Oh my gosh. Let's see the result of this, the actual result of this. 7 raised to 2 times 7 raised to 6. Got 2 over 1. Now let's try 6. 7 raised to 2 over 7. What the fuck? What the fuck? Okay. What are the steps? How did you come up with that? Yeah, it's 7 over 7. Dude, it's the same as 7 over 7. 2 times 7 to the 6 or 1. Or we can. How about if I reciprocal this 7 over 6? 7 over 3 divided by 1 over, wait, what? Can't do that. Seven raised to 6. We can multiply in any order, so it's the same shit as 7 raised to 6 times 7 raised to 2, or 7 raised to 6 times 1 over 7. Since negative 2 though. So let's do the reciprocal of that. We'll make it negative 6 over 1 over negative 6. Negative. Yo, this is a mystery. What the fuck? How the fuck? I think there's some kind of man, this is confusing. But let's erase. Why I only have this much space? So shit. 7 raised to 2 is the same as 1 over 7 raised to positive 3 times 7, 6. So we have 7, 6 over 7 to the positive 2, or 7 fourths. It's not the same shit. 4, 1. How do I even get to express that in this manner? I guess if you could say, oh man, this is hard. Let's say 7 times 1 over. We can do that, can we? 7 raised to negative 6. 7. How did you get this? Oh, I'm gonna take a screenshot of this. Now let's see the mean. Oh my god, you just found the structure, the shit. From 7 to 4, you turn it like 7 to raised to 2, so we got like that, and the reciprocal of that is gonna be like 7 2 over. Wait, what? Yo! Oh, confusing. What the fuck, dude? Where did you get these? Let's read this one more time. Okay, so let's say 7 squared. If we convert this into the thingy, positive, so we'll have 7 percent positive, 4 positive 2. And then we transpose that shit. We have 7 2 times 7 2. Okay, I kind of look for it, but how did you get How do I get from? Okay, so I guess if I have like 7, 4, and that's equivalent 7 times 7. Then put that on there. Just simply dividing by that 7 to 7. What the fuck? Insane. This is insane. I mean, if you subtract 7 2 by that, it's 7 4 backward. That's so weird. So it doesn't actually go from here to there, but from 7 4. We're checking if this is, since it's equal to the same 4, checking if this is equal to 7 4. If not, there then this one. Very cool. So 7 4 7 to convert that to thing here. It's not even equal. 7 raised to 7 1 7 raised to 7. Oh, not really. Oh, negative. Okay, cool. Same shit. Which expressions are equivalent to? Okay. Oh, 4, 5, 6 to the 5th. No. No. Yes. Yes. Oh shit. Oh no, I had a mistake. This is 6 to the 6th. We need 5, 6 to the 5. This one's. Wow, this is insanely hard. Let's see. So they have the same exponent. If they have the same exponent, then you could just multiply the base. What the fuck? Oh my god, that's insane. Wow, okay. Now that makes sense actually. So we have 6. It's just fucking refactor the shit. So just 2, 3, 5. Oh my god, it's insane. It's gonna be redistributed anyway. Yo, it's sick. So this is the same as 5 over negative 6 or 1. 6. Oh my god. Natali tried to evaluate the expression raised to 0. Cool. So just step through. Now let's see. We can't immediately just. Actually, we can. Oh. If this is the same shit, then if we just do 4 times 8, that's very much better. Because that's the same as 4 times 4 times 2 raised to negative 3. It's kind of distributed that, that's correct. No, not really. This is the same as 1 over 4 raised to 2 times 1 over 7. Or 4 times 7 raised to negative 2. Awesome, same shit. Could do 1 over 28 over 1 over 28 raised to 10. If we have 1 raised to what's that? 4 raised to times 1 over 7 raised. Oh wow, cool. Okay, so I guess oh my god, what was that? One 8 raised to 2, okay, cool. And also not this one. No. So we're looking for a factor that's something over 1, or that is the same as 28 raised to negative 2, right? How is the square? Okay, so we could say 7 negative 2 over 1 over 4 raised to 2, and we get 4 possible 1. 4. This is shaping all of that. It's 1 over 28 over 2, or 28 raised to negative. We could make it 4 times 7 raised to negative 2, that would work as well. But it doesn't seem to be the case. So from this point we could do 7 raised to negative 2 over, what's this, times, it's multiplied actually, so multiplied by 1 over 4 raised to, oh my gosh, finally. Got him. Got him. Let's see how he did. Seven raised. Or what? Three, 4, 5, 6 with 7 raised to 6. Okay, so it's the same. 7 raised to 6. This is 8 to 6. Oh wow, that's pretty easy. Let's down to this. I have a lot of video watching after this. Oh man. The reciprocal of 6 is gonna be 1 over 6 to negative 5. Then it's gonna be 2 raised to 5 divided by 6 raised to negatives. Yo, what the fuck? Okay. Then if we do that, oh my god, how did you get even 3? The fuck? Pretty sure it's not correct. This one. This is hard. Let's try to solve this first. The reciprocal of 6 to the 5th is the same as 1 over 6 to the negative 5th. To multiply that with this one, we'll have 2/5 over 6 to the negative. Yo, what if I'm... Six is two. It's very hard. I have no idea. This is insanely hard. I mean, that's what happens. If you like do what's this? then would that be the same as 2 raised to 5 times 1 over 6 raised to negative 5? Is this correct? Wow, I think I made a mistake. The reciprocal of that's... What if I don't make this negative 5? What? So I guess 6 over 5 is the same as that, and it's 1 over 6. And then what the fuck with their rule? The negative shit. So 2/5 is the same as multiply that 6 over 5, positive 5 actually. Because 2 raised to 5 is 6 raised to 5 divided by that. Raised to positive 5. This one's negative though. Oh my god, this part. What? What the? Yo, what the fuck? All of this? What? Now, oh my god. I mean, if I came up with this earlier, then it convert that to non-negative bullshit. I guess not. The 2/5 is the same as multiplying 6. 65 over 1, then we have 1 over 60 raised to 5, then 2/5 times 6 raised to negative 5. That one worked. Okay. How is this going to work though? How is it the same shit? Here. Okay. This should be our answer. What? 1/3? What the fuck? Yo, what the fuck? 2 raised to 5 dip. Huh. This will be correct, but how is this actually equivalent to this? Well, let's see. This is 6 over 5 multiplied by the reciprocal of 2 multiplied by 1 over negative 5 then I guess it's the same thing as 60 divided by. Damn, that's insane, bro. That is insane. How did you come up with that? Yes. What? 2 over 6. This is 3 raised to positive 5. What? This is blowing my mind. Oh shit. Different base, different exponents, so we'll go straight. A raised to 63 times B raised to positive 18. Okay, just one answer. Okay. We'll try to write the expression by raising. Let's see. I can subtract that with negative 2. 1 over 5 raised to positive 2. Okay. That you did not make a mistake. Negative 6 minus negative 4 would be negative 2. Right? Yep. Right. Select the equivalent expression. Okay, cool. This is the same, different base, different exponents. B raised to negative 21 over 4 raised to negative 15. I guess I could do the reciprocal of this. B positive 15 for B placed in positive. Okay, I'm pretty sure it's correct. Yeah. Let's see how we did it. Are you fucking kidding me? Are you fucking kidding me? This is step. Okay. B. It's some part here. That's okay. Expressions are equivalent to 5 raised to negative positive 12 times 5 raised to 8. Okay. Same base. This is 5 raised to 20. This is 5 raised to 20. 2 answers. 25 is not right. Let's see this one. This is 5, 3, 4, 12, 8, 16. Okay, cool. Damn, that's so insane. One other. Okay, cool. Scientific notation.
I don't think it's necessary. If one were to do any kind of science, they're going to be dealing with a lot of numbers. And I don't think it's any secret that if one were to do any kind of science, they're going to be dealing with a lot of numbers. Biology or chemistry or physics. Numbers are involved, and in many cases, the numbers are very large. There are very, very large numbers. Very large numbers. Or they're very small numbers. Very small numbers. You can imagine some very large numbers. If I were to ask you how many atoms are there in the human body, or how many cells there are in the human body, or the mass of the Earth in kilograms, those are very large numbers. If I were to ask you the mass of an electron, that would be the human body, or the mass of the Earth in kilograms. Those are very large numbers. If I were to ask you the mass of an electron, that would be a very, very small number. So in any kind of science, we're going to be dealing with these. Just as an example, let me show you one of the most common numbers you're going to see, and especially chemistry. It's called Avogadro's number. Avogadro's number. And if I were to write it in just the standard way of writing a number, it would literally be written as, in color, it would be 6, 0, 2, 2, and then another 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And even if I were to throw some commas in here, it's not going to really help the situation to make it more readable. Just throw some commas in here. It's still a huge number, and I don't even, if I had to write this on a piece of paper, or if I were to publish some paper on, using Avogadro's number, it would take me forever to write this, and even more, it's hard to tell if I forgot to write a 0, or if I maybe wrote too many zeros. So there's a problem here. Is there a better way to write this? So is there a better way to write this than to write it all out like this? To write literally the 6 followed by the 23 digits, or the 6022 followed by the 20 zeros there. And to answer that question, and in case you're curious, Avogadro's number, if you have 12 grams of carbon, especially 12 grams of carbon-12, this is how many atoms you would have in that. And just so you know, 12 grams is a 50th of a pound. So that just gives you an idea of how many atoms are laying around at any point in time. This is a huge number. That's the point of here is that the teacher in chemistry, the point of here is the grams of carbon. In case you're curious, Avogadro's number, if you have 12 grams of carbon, especially 12 grams of carbon-12, this is how many atoms you would have in that. And just so you know, 12 grams is like a 50th of a pound. So that just gives you an idea of how many atoms are laying around at any point in time. This is a huge number. That's the point of here is that the teacher in chemistry, the point of here is to talk about an easier way to write this. And the easier way to write this we call scientific notation. Scientific notation. And take my word for it, although it might be a little unnatural for you at this video, it really is an easier way to write things like that. So let me, before I show you how to do it, let me show you the underlying theory behind scientific notation. If I were to tell you what is 10 to the 0 power, you know that's equal to 1. What is 10 to the 1 power? That's equal to 10. It's 10 squared. If I were to, let me show you the things like before it, things like that. So let me, before I show you how to do it, let me show you the underlying theory behind scientific notation. If I were to tell you what What is 10 to the 0 power? We know that's equal to 1. What is 10 to the 1 power? 10. What's 10 squared? That's 10 times 10. That's 100. What is 10 to the third? 10 to the third is 10 times 10 times 10, which is equal to 1,000. I think you see a general pattern here. 10 to the 0 has no zeros. No zeros in it, right? 10 to the 1 has 1 0. 10 to the 10 to the second power, this is the 2th power. 10 to the second power has 2 zeros. Finally, 10 to the third has 3 zeros. I don't want to beat a dead horse here, but I think you get the idea. 3 zeros. If I were to do 10 to the 100th power, 10 to the 100th power, what would that look like? I don't feel like writing it all out here, but it would be 1 followed by, you could guess it, 100 zeros. It would just be a bunch of zeros. If we were to count up all of those zeros, we would have 100 zeros right there. Actually, this might be interesting.
3, 6, 9,
just as an aside, you may or may not know what this number is called. This is called a Google. A Google. In the early 90s, if someone said, "Hey, that's a Google," you wouldn't have thought of a search engine. You would have thought of the number 10 to the 100th power, which is a huge number. If you actually, it's more than the number of atoms, or the estimated number of atoms in the known universe. In the known universe, I mean, the estimated number of atoms. It's more than the number of atoms, or the estimated number of atoms in the known universe. In the known universe, I mean, it's a question of what else we could get out there, but in the known universe, I mean, it's a question of what else we could get out there, but I was reading up on this not too long ago, and if I remember correctly, the known universe has the order 10 to the 79th to 10 to the 81 atoms. And this is, of course, rough. No one can really count those. People are just kind of estimating it, or even better, guesstimating it. This is a huge number, but maybe even more interesting to you, this number was the motivation behind naming a very popular search engine, Google. Google. Google is essentially just a misspelling of the word Google with the O-L. And I don't know why they called it Google. Maybe they got the domain name. Maybe they want to hold this much information, maybe that many bytes of information, or it's just a cool word. Whatever it is, maybe it was the founder's favorite number, but it's a cool thing. But anyway, I'm digressing. This is a Google. It's just 1 with 100 zeros. But I could equivalently have just written that as 10 to 100, which is, clearly an easier way. This is an easier way to write this. This is easier. In fact, this is so hard to write that I didn't even take the trouble to write it. It would have taken me forever. This is just 20 zeros right here. 100 zeros I would have filled up, and I would have filled up the screen, and you would have found it boring. So I didn't even write it. So clearly, this is easier to write. And so you might think, well, how can we write? This is just good for powers of 10, right? But how can we write something that isn't a direct power of 10? How can we use the power of this simplicity? How can we use the power of this simplicity somehow? And to do that, you just need to make the realization. This number, we can write it as, that it can be write. This is easier to write. And so you might think, well, how can we write? This is just good for powers of 10, right? And how can we write something, how can we write, this is just good for powers of 10, right? And how can we write something that isn't a direct power of 10? How can we use the power of this simplicity? How can we use the power of this simplicity somehow? And to do that, you just need to make the realization. This number, we can write it as, so this has how many digits in it? It has 1, 2, 3, and then 20 zeros. So it has 23 digits after the 6, right? 23 digits after the 6. So what happens if I have
1, 2, 3, 4, 5, 6, 6, 3, 18, 19, 20. 1, 2, 3, 1, 3.
If I use this, if I try to get close to it with the power of 10. But what if I were to say 10 to the 23, this magenta? 10 to the 23rd power, that's equal to what? That equals 1 with 23 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 15, 16, 17, 18, 19, 20, 21, 22, 23. You get the idea. That's 10 to the
Times 10
23rd.
raised to 23.
Now, can we somehow write this guy as some multiple of this guy? Well, we can, because if we multiply this guy by 6, so what is 6? If we multiply 6 times 10 to the 23rd, what do we get? Well, we're just going to have a 6 with 23 zeros. We're going to have a 6, and then you're going to have 23 zeros. 23 zeros. So all I did, if you take 6 times this, you don't have to multiply, you have 6 times this 1, and you get a 6, and then all the 6 times the zeros will all be zeros. So that's 6 followed by 23 zeros. So that's pretty useful, but still we're not getting quite to this number. I mean, this had some 2's in there, so how can we do it a little bit better? Well, what if we wrote it as a decimal? This number right here, is identical to this number as if these 2's were zeros. But if we want to put those 2's there, what can we do? We can put some decimals here. If we want to put those 2's there, what can we do? It's identical to this number as if these 2's were zeros. But if we want to put those 2's there, what can we do? We can put some numbers as decimals. This number right here is identical to this number as if these 2's were zeros. But if we want to put those 2's there, what can we do? We can put some decimals here. We can say that this is the same thing as 6.022 times 10 to the 23rd. And now this number is identical to this number, but it's a much easier way to write it. And you could verify it if you like. It'll take you a long time. Maybe you should do the smaller number first. If you multiply 6.022 times 10 to the 23rd, and you write it all out, you will get this number right there. You will get Avogadro's number. Avogadro's number. And although this is complicated, or it looks a little bit unintuitive to you at first, this is just a number written out. This has a multiplication and then a 10 to a power. And I say, hey, that's not so simple, but it really is, because you immediately know how many zeros there are, and it's obviously a much shorter way to write this number. Let's do a couple of more. I started with Avogadro's number because it really shows you the need for a scientific notation, so you don't have to write things like that. So let's do a couple of other numbers, and we'll just write them in scientific notation. Let's say I have the number 7,345, and I want to write it in scientific notation. So I guess the best way to think about it is 7,000
times 10 raised to the
So how can I represent kind of 1,000?
7.345
10 to the third is
raised to the
1,000. So we know that 10 to the third is equal to 1,000. So that's essentially the largest power of 10 that I can fit into this. This is 7,000. So if this is 7,000, but then it's 0.3,000, then it's 0.04,000. I don't know if that helps you. We can write this as 7.345 times 10 to the third. So it's going to be 7,000 plus 0.3,000. What's 0.3 times 1,000? 0.3 times 1,000 is 300. What's 0.04 times 1,000? That's 40. What's 0.005 times 1,000? That's a 5. So 7.345 times 1,000 is equal to 7,345. Let me multiply it out just to make it clear. So if I took 7.345 times 1,000, the way I do it is I ignore the zeros. I essentially multiply 1 times that guy up there. So I get 7,345. Then I have 3 zeros here, so I put those on the end. And then I have 3 decimal places. 1, 2, 3. So 1, 2, 3, put the decimal right there. And there you have it. 7.345 times 1,000 is indeed 7,345. Let's do a couple of them. Let's say we wanted to write the number 6 in scientific notation. Obviously, there's no need to write in scientific notation, but how would you do it? Well, what's the largest power of 10 that fits into 6? Well, the largest power of 10 that fits into 6 is just 1. So we could write it as something times 10 to the 0. This is just 1, right? That's just 1. So 6 is what times 1? This is 6. So 6 is equal to 6 times 10 to the 0. You wouldn't actually have to write it this way. This is much simpler, but it shows you that you really can express any number in scientific notation. Now, what if we wanted to represent something like this? I started off the video saying in science, you deal with very large and very small numbers. So let's say you had the number do it in this color. Say the number 1, and you have 1, 2, 3, 4, and then let's say 5 zeros, and then you have followed by a 7. Once again, this is not an easy number to deal with, but how can we deal with it as a power of 10? As a power of 10. So what's the largest power of 10 that fits into this number? This number is divisible. Let's think about it. All the powers of 10 we did before were going to positive, or going to, positive powers of 10. We could also do negative powers of 10. We know that 10 to the 0 is 1. Let's start there. 10 to the minus 1 is equal to 1 over 10, which is equal to 0.1. Let's switch colors. I'll do pink. 10 to the minus 2 is equal to 1 over 10 squared, which is equal to 1 over 100, which is equal to 0.01. And I think you get the idea that well, let me just do one more so that you can get the idea. 10 to the minus 3. 10 to the minus 3 is equal to 1 over 10 to the third, which is equal to 1 over 1,000, which is equal to 0.001. So the general pattern here is 10 to the whatever negative power is however many places you're going to have behind the decimal point. So here, it's not the number of zeros. Then here, it's 10 to the minus 3. You only have 2 zeros. We have 3 places behind the decimal point. So what is the largest power of 10 that it goes into this? Well, how many decimal places behind the decimal point do I have? I have 1, 2, 3, 4, 5, 6. So 10 to the minus 6 is going to be equal to point, and we're going to have 6 places behind the decimal point, and the last point is going to be, or the last place is going to be a 1. So you're going to have 5
consider
zeros
the first 0
and a 1. That's 10 to the minus 6. Now this number right here is 7 times this number, right? If we multiply this times 7, we get 7 times 1, and then we have 1, 2, 3, 4, 5, 6 numbers behind the decimal point. So 1, 2, 3, 4, 5, 6. So this number times 7 is clearly equal to the number that we started off with. So we can rewrite this number. Instead of writing this number every time, we can write it as being equal to this number, or we could write it as 7. This is equal to 7 times this number. But this number is no better than that number, but this number is the same thing as 10 to the minus 6. 7 times 10 to the minus 6. So now you can imagine, numbers like, imagine the number, what if we had a 7, let me think of it this way. What if we had a 7, so we had a 7, 3 over there. So what would we do? Well, we'd want to go to the first digit right here, because this is kind of the largest power of 10 that could go into this thing right here. So if we wanted to represent that thing, let me do another decimal that's like that. So let's say it was 0.0000516, and I wanted to represent this in time notation. I'd go to the first non-digit
5.16.
first non-zero digit,
raised to negative 5.
Non-digit 0, which is there. I'm like, okay, what's the largest power of 10 that'll fit into that? So I go 1, 2, 3, 4, 5. So it's going to be equal to 5.16. I take 5 there, and then everything else is going to be behind the decimal point, times 10. So this is going to be the largest power of 10 that fits into this first non-zero number. It's 1, 2, 3, 4, 5, so 10 to the minus 5 power. Let me do another example. So the point I wanted to make is you just go to the first, if you're starting at the left, the first non-zero number, that's what you get your power from. That's where I got my 10 to the minus 5, because I counted 1, 2, 3, 4, 5. You got to count that number, just like we did over here. And then everything else will be behind the decimal. Let me do another example. It's a point, my wife always points out that I have to write a 0 in front of my decimal points, because she's a doctor, and if people don't see the decimal point, someone might overdose on some medication. So let's write it her way. 0.0000000008192. Clearly, this is a super cumbersome number to write, and you might forget about a 0 or add too many zeros, which could be costly if you're doing some important scientific research, or maybe you wouldn't prescribe medicine at this small dose, but maybe you will. I don't want to get into that. But how would I write this in scientific notation? So I start off with the first non-zero number if I'm starting from the left. So it's going to be 8.192. I just put a decimal and write 0.192 times 10 to the what? I just count. Times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to include that number, 10 to the minus 10. And I think you'll find it reasonably satisfactory that this number is easier to write than that number over there. Now, and this is another powerful thing about scientific notation. Let's say I have these two numbers and I want to multiply them. Let's say I want to multiply the number 0.005 times the number 0.0008. This is actually a fairly straightforward one to do, but sometimes it can get quite cumbersome, especially if you're dealing with 20 or 30 zeros on either side of the decimal point. Zero here to make my life happy. But when you do it in scientific notation, it'll actually simplify it. This guy can be rewritten as 5 times 10 to the what? I have 1, 2, 3 spaces behind the decimal, 10 to the third. And then this is 8, so this is times 8 times 10 to the, sorry, this is 5 times 10 to the minus 3. That's very important. 5 times 10 to the 3 would have been 5,000. Be very careful about that. Now, what does this guy equal to? This is 1, 2, 3, 4 places behind the decimal, so it's 8 times 10 to the minus 4. So if we're multiplying numbers, so this is, if we're multiplying these two things, this is the same thing as 5 times 10 to the minus 3 times 8 times 10 to the minus 4. There's nothing special about the scientific notation. It literally means what it's saying. So if we're multiplying, you can write it out like this. And multiplication, order doesn't matter, so I can rewrite this as 5 times 8 times 10 to the minus 3 times 10 to the minus 4. And then what is 5 times 8? 5 times 8, we know, is 40. So 40 times 10 to the minus 3 times 10 to the minus 4. And if you know your exponent rules, you know that when you multiply two numbers that have the same base, you can just add their exponents. You just add the minus 3 and the minus 4. So it becomes equal to 40 times 10 to the minus 7. Let's do another example. Let's say we were to multiply Avogadro's number. So we know that 6.022 times 10 to the 23rd. Let's say we were to multiply that times some really small number. So times, let's say 7.23 times 10 to the minus 22. So this is some really small number. You're going to have a decimal, and then you're going to have 21 zeros, then you're going to have a 7, and then 2 and a 3. So this is some really small number. But the multiplication, when you do it in scientific notation, is actually very straightforward. This is going to be equal to 6.0, let me write it properly, 6.022 times 10 to the 23rd times 7.23 times 10 to the minus 22. We can change the order. So it's equal to 6.022 times 7.23. That's that part, so you can do it as the first part of our scientific notation, times 10 to the 23rd times 10 to the minus 22. Now, this is, you're going to do some decimal multiplication right here. It's going to be some number, 40 something, I think. I can't do this one in my head. But this part is pretty easy to calculate. I'll just leave this as the way it is. But this part right here, this will be times 10 to the 23rd times 10 to the minus 22. You just add the exponents. You get times 10 to the first power times 10. And then this number, whatever it's going to equal, I'll just leave it out here because I don't have a calculator. 0.23, let's see, it would be 7.2, let's see, 0.2 times to the fifth, it would be like 41 something. So this is approximately 41 times 10 to the 1, or another way, it's approximately, it's going to be 410 something. And to get it right, you just have to actually perform this multiplication. So hopefully you see that scientific notation is one really useful for super large and super small numbers, and it's not only is it more useful to kind of understand the numbers and to write numbers, but it also simplifies operating numbers into
Three.
It helps understand them.
way to write this we call scientific notation. Scientific notation. And take my word for it, although it might be a little times 10 to the 1, 2, 3, 4, 5, 6, 7. It always helps me to see a lot of examples of something, so I figured
I'm gonna take a bit of a break. I'm just gonna buy a snack. Alright, I'm back.
it always helps me to see a lot of examples of something, so I figured it wouldn't hurt to do more scientific notation examples. So I'm just going to write a bunch of numbers and then write them in scientific notation, and hopefully this will cover almost every case you'll ever see. And then at the end of this video, we'll actually do some computation with them, just to make sure that we can do computation with scientific notation. We'll just write down a bunch of numbers. So 0.00852. That's my first number. My second number is 7, 0,
Oh man, I love the
1,
soda.
2, 0, 0, 0, 0,
It's orange soda.
0. Arbitrarily stopping the zeros. The next number is 0.0000000. I'll just draw a couple more. Keep saying 0. You might find that annoying. 5, 0, 0. The next number right here, there's a decimal right there. The next number I'm going to do is the number 7, 2, 3. The next number I'll do, I have a lot of 7s here, let's do 0.6. And let's do 0.6. And then let's just do one more just to make sure we've covered all of our bases. Let's say we do 8, 2, 3, and then let's throw some arbitrary numbers here right there. So this first one, right here, what we do is we want to write in scientific notation. We want to figure out the largest exponent of 10 that fits into it. So we go to the first non-zero term, which is that right there. We count how many positions to the right of the decimal point we have, including that term. So we have 1, 2, 3. So it's going to be equal to this. So it's going to be equal to 8. That's that guy right there, 0.52. So everything after that first term is going to be behind the decimal, so 0.52 times 10 raised to the number of terms we have. 1, 2, 3. 10 to the minus 3. So when you think of it, this is a little bit more. This is like 8.5 thousandths, right? Each of these is thousands. We have 8.5. Let's do this one. Let's see how many zeros we have. We have 3, 6, 9, 12. So we want to do again, we start with our largest term that we have, our largest non-zero term. This is going to be the term all with the left. That's our 7. So it's going to be 7.012. It's going to be equal to 7.012 times 10 to the what?
10
So it's going to be times 10 to the 1 with this many zeros. So how many things? We had a 1 here. And we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. Now I want to be very clear, you're not just counting the zeros, you're counting everything after this first term right there. So it would be equal to a 1 followed by 12 zeros. So it's times 10 to the 12. Just like that, not too difficult. Let's do this one right here. So we go behind our decimal point, we find the first non-zero number, that's our 5. So it's going to be equal to 5. There's nothing to the right of it, it's 5.00 if we wanted to add some precision to it. But it's 5 times, and then how many numbers to the right or behind to the right of the decimal do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and we have to include this one, 14. So 5 times 10 to the minus 14th power. Now this number, you might be able to overkill to write this in scientific notation, but it never hurts to get to practice. So what's the largest 10 that goes into this? Well, 100 will go into this. And you could figure out 100 or 10 squared by saying, okay, this is our largest term. And then we have 2 zeros behind it, because 100 will go into 723. So this is going to be equal to 7.23 times, we could say times 100, but we want to say in scientific notation, so we'll write times 10 squared. Now we have this character right here. What's our first non-zero
Into the
term?
negative.
That one right there.
6 times 10
And
raised
then
to
how many terms do we have to write at the decimal? We have only one. So times 10 to the minus 1. That makes a lot of sense. But that's essentially equal to 6 divided by 10. 10 to the minus 1 is 1 over 10, which is 0.6. One more. Let me throw some commas here just to make this a little easier to look at. So let's take our largest value right there. We have our 8. So it's going to be
raise
0.23. 8.23. We don't have to add the other stuff. Times 10 to the, well, we just count how many terms there are after the 8.
10 raised to 10.
1, 2, 3, 4, 5, 6, 7, 8, 9,
10 raised to 10.
8.23 times 10 to the 10. I think you get the idea. Now it's pretty straightforward, and more than just being able to calculate it, which is a good skill by itself. I want you to understand why this is the case. Hopefully that last video explained it, and if it doesn't, just multiply this out. Literally multiply 8.23 times 10 to the 10, and you will get this number. Then you can try it with something smaller than 10 to the 10, 10 to the 5th, and we'll get a different number. We'll end up with 5 digits after the 8. But anyway, let me do a couple of more computation examples. Let's say we had the numbers. Let me just make them really small. 6, 4
times 6.4 times 10 raised to 6.
Multiply it. I want to multiply it by, let's say I have a really large number. 3, 2,
Shit. We have a bunch of
zeros here. Stop. Let's say I stop there. So this one you could multiply out, but it's, you have to count both. It's a little difficult, but let's put it in the scientific notation. One, it'll be easier to represent these numbers, and hopefully you'll see that the multiplication actually gets simplified as well. So this top guy right here, how can we write him in scientific notation? It would be 6.4. 6.4 times 10 to the what? 1, 2, 3, 4, 5, 6. I have to include the 6. So times 10 to the minus 6. And what can this one be written as? This one is going to be 3.2, right? 3.2. And then you count how many digits are after the 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 3.2 times 10 to the 11. So if we multiply these two things, this is equivalent to 6. Color. Is equivalent to 6.4 times 10 to the minus 6 times 3.2 times 10 to the 11, which we saw in the last video is equivalent to 6.4 times 3.2. I'm just changing the order of our multiplication. Times 10 to the minus 6 times 10 to the 11th power. Now what will this be equal to? Well, to do this, I don't want to use a calculator, so let's just calculate it. So 6.4 times 3.2. Let's ignore the decimals for a second. We'll worry about that at the end. So 2 times 4 is 8. 2 times 6 is 12. Nowhere to carry the 1, so it's just 128. Put a 0 down there. 3 times 4 is 12. Carry the 1. 3 times 6 is 18. We got a 1 there, so it's 192. Right? Yeah, 192. You add them up, you get 8. 4. 1 plus 9 is 10. Carry the 1, you get 2. Now, we just have to count the numbers behind the decimal point. We have one number there, we have another number there. We have 2 numbers behind the decimal point. So you count 1, 2. So 6.4 times 3.2 is equal to 20.48. So this is going to be 20.48 times 10 to the, we have the same base here, so we can just add the exponents. So what's minus 6 plus 11? So 10 to the 5th power, right? Right, minus 6 and 11. 10 to the 5th power. And so the next question, I say, oh, I'm done. I've done the computation, and you have, and this is a valid answer. So the next question is this in scientific notation? And if you wanted to be...
I just have some weird... what's this? 3 raised to 4 times 5 raised to 4. And we'll have it's be the same. Wow.
Going to be a real stickler about it. It's not in scientific notation because we have something here that could maybe be simplified a little bit. We could write this. Let me do it this way. Let me divide this by 10. So any number we can multiply and divide by 10. So we could write it this way. We could write 1 over 10 on this side, and we could multiply times 10 on that. Right? That shouldn't change the number. You divide by 10 and multiply by 10. It's just like multiplying by 1 or dividing by 1. So if you divide this side by 10, you get 2.048. When you multiply that side by 10, you get to times 10 to the, times 10 is just times 10 to the first. You just add the exponents, times 10 to the 6. And now if you're a stickler about it, this is good scientific notation right there. Right there. I've done a lot of multiplication. Let's do some division. Let's divide this guy by that guy. So if we divide, we have 3.2 times 10 to the 11th power divided by 6.4 times 10 to the minus 6. What is this equal to? Well, this is equal to 3.2 over 6.4. We can just separate them out because it's associative. So we can say this times 10 to the 11th over 10 to the minus 6, right? If you multiply these two things, you'll get that right there. So 3.2 over 6.4, this is just equal to 0.5, right? 32 is half to 64, or 3.2 is half to 6.4. So this is 0.5 right there. What is this? This is 10 to the 11th over 10 to the minus 6. So when you have something in the denominator, you could write it this way. This is equivalent to 10 to the 11th over 10 to the minus 6 is equal to 10 to the 11th is equal times 10 to the minus 6 to the minus 1. So this is equal to 10 to the 11th times 10 to the 6. What did I do just there? This is 1 over 10 to the minus 6. So 1 over something is just that something to the negative 1 power when I multiply the exponent. You can think of it that way, so this is equal to 10 to the 17th power, 10 to the 17th power. Or another way to think about it is if you have one that have the same bases, 10 in this case, and you're dividing them, you just take the one in the numerator and you subtract the exponent in the denominator. So it's 11 minus 6, which is 11 plus 6, which is equal to 17. So this division problem ended up being equal to 0.5 times 10 to the 17, which is the correct answer. But if you wanted to be a stickler and put in the scientific notation, we want something maybe greater than 1 right here. So the way we can do that, let's multiply by 10 on this side. Let's multiply by 10 on this side and divide by 10 on this side. We'll multiply by 1 over 10. Remember, we're not changing the number if you multiply by 10 and divide by 10. We're just doing it to different parts of the product. So this side is going to become 5. Pink. This side is going to become 5, right? 10 times 0.5 is 5, times 10 to the 17th divided by 10. That's the same thing as 10 to the 17th times 10 to the minus 1, right? That's 10 to the minus 1. So it's equal to 10 to the 16th power. 10 to the 16th power, which is the answer when you divide these two guys right there. So hopefully these examples have filled in all of the gaps or the uncertain scenarios dealing with scientific notation. If I haven't covered something, feel free to write a comment on this video or pop me an email.
I'll do that.
There are two whole Khan Academy videos on what scientific notation is, why we even worry about it, and also goes through a few examples. And what I want to do in this video is just use the ck12.org Algebra 1 book to do some more scientific notation examples. So let's take some things that are written in scientific notation. Just as a reminder, scientific notation is useful because it allows us to write really large or really small numbers in ways that are easy for our brains to, 1, write down, and 2, understand. So let's write down some numbers. So let's have 3.102 times 10 to
to the second. And I want to write it as just a numerical value. It's in scientific notation already. It's written as a product with a power of 10. So how do I write this as just a numeral? Well, there's a slow way and the fast way. The slow way is to say, well, this is the same thing as 3.102 times 100, which means if you multiply 3.102 times 100, it'll be 3102 with 2 zeros behind it. And then we have 1, 2, 3 numbers behind the decimal point. 1, 2, 3 numbers behind the decimal point. And that would be the right answer. This is equal to 310.2. Now, a faster way to do this is just to say, well, look, right now I have only the 3 in front of the decimal point. When I take something to the times 10 to the second power, I'm essentially shifting the decimal point 2 to the right. So 3.102 times 10 to the second power is the same thing as, if I shift the decimal point 1 and then 2, because this is 10 to the second power, it's the same thing as 310.2. So this might be a faster way of viewing it. Every time you multiply it by 10, you shift the decimal to the right by 1. Let's do another example. Let's say I had 7.4 times 10 to the 4th. Well, let's just do this the fast way. Let's shift the decimal 4 to the right. So 7.4 times 10 to the 4th times 10 to the 1, you're going to get 74. Then times 10 to the second, you're going to get 740. We're going to have to add a 0 there because we have to shift the decimal again. 10 to the third, you're going to have 7,400. And then 10 to the 4th, you're going to have 74,000. Notice I just took this decimal, went 1, 2, 3, 4 spaces. 4 spaces. So this is equal to 74,000. And when I had 74 and I had to shift the decimal 1 more to the right, I had to throw a 0 here. I'm multiplying it by 10. Another way to think about it is I need 10 spaces between the decimal, between the leading digit and the decimal. So right here I only have 1 space. I'll need 4 spaces. So 1, 2, 3, 4. Let's do a few more examples. I think the more examples, the more you'll get what's going on. So I have 1.75 times 10 to the negative 3. This is in scientific notation. 5 examples. So 1 decimal. So right here in the decimal, between the leading digit and the decimal. So right here I only have 1 space. I'll need 4 spaces. So 1, 2, 3, 4. Let's do a few more examples. I think the more examples, the more you'll get what's going on. So I have 1.75 times 10 to the negative 3. This is in scientific notation, and I want to just write the numerical value of this. So when you take something to the negative times 10 to the negative power, you shift the decimal to the left. So this is 1.75. So if you do it times 10 to the negative 1 power, you will go 1 to the left. But if you do times 10 to the negative 2 power, you'll go 2 to the left. You have to put a 0 here. And if you do times 10 to the negative 3, you go 3 to the left. And you would have to add another 0. So you take this decimal and go 1, 2, 3 to the left. So our answer would be 0.00175 is the same thing as 1.75 times 10 to the negative 3. And another way to check that you got the right answer is if you have a 1 right here, if you count the 1 including the zeros to the right of the decimal should be the same as the negative exponent here. So you have 1, 2, 3 numbers behind the decimal. So you should have, that's the same thing as to the negative 3 power. You're doing 1,000. So this is 1,000 right there. Let's do another example. Actually, let's mix it up. Let's start with something that's written as a numeral and then write it in scientific notation. So let's say I have 120,000. So that's just this numerical value. And I want to write it in scientific notation. So this I can write as, I take the leading digit, 1.2 times 10 to the, and I just count how many digits there are behind the leading digit. 1, 2, 3, 4, 5. So 1.2 times 10 to the 5th. And if you want to handle it, internalize why that makes sense. 10 to the 5th is 10,000. So 1.2, 1.2, 10 to the 5th is 100,000. So it's 1.2 times 1, 2, 3, 4, 5. You have 5 zeros. It's 10 to the 5th. So 1.2 times 100,000 is going to be 120,000. It's going to be 1 1/5 times 100,000, so 120. Hopefully that's sinking in. So let's do another one. Let's say the numerical value is 1,761,000 times the leading numerical value. Let's say I have 120,000. So that's just this numerical value, and I want to write it in scientific notation. So this I can write as, I take the leading digit, 1.2 times 10 to the, and I just count how many digits there are behind the leading digit. 1, 2, 3, 4, 5. So 1.2 times 10 to the 5th. And if you want to handle it, internalize why that makes sense. 10 to the 5th is 10,000. So 1.2, 1.2, 10 to the 5th is 100,000. So it's 1.2 times 1, 2, 3, 4, 5. You have 5 zeros. It's 10 to the 5th. So 1.2 times 100,000 is going to be 120,000. It's going to be 1 1/5 times 100,000, so 120. Hopefully that's sinking in. So let's do another one. Times 100 times 100,000 is going to be 120,000. It's going to be 1 1/5 times 100,000, so 120. Hopefully that's sinking in. So let's do another one. Let's say the numerical value is 1,765,244. I want to write this in scientific notation. So I take the leading digit, 1, put a decimal sign, everything else goes behind the decimal, 7, 6, 5, 2, 4, 4. And then you count how many digits there were between the leading digit, and I guess you could imagine the first decimal sign, because you could have numbers that keep go over here. So between the leading digit and the decimal sign. And you have 1, 2, 3, 4, 5, 6 digits. This is times 10 to the 6th. And 10 to the 6th is just a million, so it's 1.765244 times a million, which makes sense. Roughly 1.7 times a million is roughly 1.7 million. This is a little bit more than 1.7 million, so it makes sense. Let's do another one. How do I write 12 in scientific notation? Same drill. It's equal to 1.2 times, we only have one digit between the 1 and the decimal spot, or the decimal point. So it's 1.2 times 10 to the first power, or 1.2 times 10, which is definitely equal to 12. Let's do a couple of examples where we're taking 10 to the negative power. So let's say we had 0.00281. We want to write this in scientific notation. So what you do is you just have to think, well, how many digits are there to get to the include the leading numeral in the value. So what I mean there is count 1, 2, 3. So what we want to do is remove the decimal 1, 2, 3 spaces. So one way you could think about it is you could multiply, to move the decimal to the right 3 spaces, you would multiply it by 10 to the 3rd. But if you're multiplying something by 10 to the 3rd, you're changing its value. So you also have to multiply by 10 to the negative 3. Only this way will you not change the value, right? If I multiply by 10 to the 3 times 10 to the negative 3, 3 minus 3 is 0. This is just like multiplying it by 1. So what is this going to equal? If I take the decimal and I move it 3 spaces to the right, this part right here is going to be equal to 2.81, and we're left with this one, times 10 to the negative 3. Now, a very quick way to do it is just to say, look, let me count, including the leading numeral, how many spaces I have behind the decimal. 1, 2, 3. So it's going to be 2.81 times 10 to the negative 1, 2, 3 power. Let's do one more like that. Let me actually scroll up here. Let's do one more like that. Let's say I have 1, 2, 3, 4, 5, 6. How many zeros do I have in this problem? Well, I'll just make up something. 0, 2, 7. And you want to write that in scientific notation. Well, you count all the digits up to the 2 behind the decimal. So 1, 2, 3, 4, 5, 6, 7, 8. So this is going to be 2.7 times 10 to the negative 8th power. Now let's do another one where we start with the scientific notation value and we want to go to the numeric value, just to mix things up. So let's say you have 2.9 times 10 to the negative 5th. So one way to think about it is this leading numeral plus all the zeros to the left of the decimal spot is going to be 5 digits. You have a 2 and a 9, and then you're going to have 5, and then you're going to have 4 more zeros. 1, 2, 3, 4, and then you're going to have your decimal. And how did I say no 4 zeros? So I'm counting this as 1, 2, 3, 4, 5 spaces behind the decimal, including the leading numeral. And so it's 0.000029. And just to verify, I do the other technique. How do I write this in scientific notation? I count all of the digits, all of the leading zeros behind the decimal, including the leading non-zero numeral. So I have 1, 2, 3, 4, 5 digits. So it's 10 to the negative 5. So it'll be 2.9 times 10 to the negative 5. And once again, I want to, this isn't just some type of black magic here. This actually makes a lot of sense. If I wanted to get this number to 2.9, what I would have to do is move the decimal over 1, 2, 3, 4, 5 spots, like that. And to get something, the decimal to move over to the right by 5 spots, I'll have to, so say with 0.00029, if I multiply it by 10 to the 5th, I'm also going to have to multiply it by 10 to the negative 5. So I don't want to change the number. This right here is just multiplying something by 1. 10 to the 5th times 10 to the negative 5 is 1. So this right here, this part right here, is essentially going to move the decimal 5 to the right. 1, 2, 3, 4, 5. So this will be 2.5, and then we're going to be left with times 10 to the negative 5. Anyway, hopefully you found that scientific notation drill useful.
Wait, I should report this.
There are two. I want to change the number. This right here is just multiplying something by 1. 10 to the 5th times 10 to the negative 5 is 1. So this right here, this part right here, is essentially going to move the decimal 5 to the right. 1, 2, 3, 4, 5. So this will be 2.5, and then we're going to be left with times 10 to the negative 5. Anyway, hopefully you found that scientific notation drill useful. Express 0.00000.
I'm missing it. Okay, cool.
0, express 0.00000003457 in scientific notation. So let's just remind ourselves what it means to be in scientific notation. Scientific notation will be some number times some power of 10, where this number right here is going to be, let me write it this way, it's going to be greater than or equal to 1, and it's going to be less than 10. So over here, what we want to put here is that the leading number is going to be, and in general you're going to look for the first non-zero digit, and this is the number that you're going to want to start off with. This is the only number you're going to want to put ahead of, I guess, to the left of the decimal point. So we could write 3.457. 3.457. And it's going to be multiplied by 10 to something. Now let's think about what we're going to have to multiply it by. To go from 3.457 to this very, very small number, I mean, we would have had to move the decimal from 3.457 to get to this. You have to move the decimal to the left a bunch. You have to add a bunch of zeros to the left of the 3. You have to keep moving the decimal over to the left.
to do that, we're essentially making the number much smaller. So we're not going to multiply it by a positive exponent of 10. We're going to multiply it times a negative exponent of 10. That the equivalent is you're kind of dividing by a positive exponent of 10. And so the best way to think about it, when you move an exponent 1 to the left, you're dividing by 10, which is equivalent to multiplying by 10 to the negative 1 power. Let me give you an example here. So if I have 1 times 10 is clearly just equal to 10. 1 times 10 to the negative 1, that's equal to 1 times 1 over 10, which is equal to 1 over 10. 1 times, let me actually write a decimal, which is equal to 0, which is equal to, I skipped a step right there. Let me add 1 times 10 to the 0, so we have something natural. So this is 1 times 10 to the first. 1 times 10 to the 0 is equal to 1 times 1, which is equal to 1. 1 times 10 to the negative 1 is equal to 1 over 10, which is equal to 0.1. If I do 1 times 10 to the negative 2, 10 to the negative 2 is 1 over 10 squared, or 1 over 100. So this is going to be 1 over 100, which is 0.01. What's happening here? When I raise it to a negative power, I raise it to a negative 1 power, I've essentially moved the decimal from to the right of the 1 to the left of the 1. I moved from there to there. When I raise it to the negative 2, I moved it 2 over to the left. So how many times are we going to have to move it over to the left to get this number right over here? So let's think about how many zeros we have. So we have to move it 1 time just to get in front of the 3, and then we have to move it that many more times to get all of the zeros in there. So that we have to move it 1 time to get the 3. So if we started here, we're going to move 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So this is going to be 3.457 times 10 to the negative 10 power. Let me just rewrite it. So 3.457 times 10 to the negative 10 power. So in general, what you want to do is you want to find the first non-zero number here. Remember, you want a number here that's between 1 and 10, and it can be equal to 1, but it has to be less than 10. 3.457 definitely fits that bill. It's between 1 and 10. Yep. And then you just want to count the leading zeros between the decimal and that number and include the number, because that tells you how many times you have to shift the decimal over to actually get this number up here. So we have to shift this decimal 10 times to the left to get this thing up here.
Maze balls. Okay, next are okay, cool. Let's see. A scientific notation. A number is cited where there's a number greater than or equal to 1, but less than 10 multiplied by a power of 10. The following numbers are in scientific notation. Okay. This video, do the same thing. Oh, I couldn't watch it. Right. Oh yeah. Let's see these. Power of 10. Oh wow! Oh. 5.8 raised to 10 negative 3. Cool. Okay, that's 2.456 raised times 10. Raised to 10. Yes. 369. It's actually 11. Check. Okay, we have 2.077 times 10 raised to 4. Looks 4? No. 2.077 times 10. What? Oh, negative 4. Shit, negative. Oh, negative. Oh, 9 point. Standard form 6, 9, 6, 6 or 7, 1, 2, 3, 4. It's gonna be just 1, 0.1, 8, 8. Orders of magnitude. Computing with scientific quiz 5 in the units. Okay, cool. Let's do it. Very cool. The question number is standard form. Okay, cool. Let's do then former 1, 2, 3, 4. 9, 10 thousandths. Holy shit. 9, 10 thousandths is this. Tens, hundreds, thousands. 9, 10. What? 10 thousandths. Oh no, it's actually this. Tens, hundreds, thousands, 10 thousandths, 9, 10 thousandths. In scientific notation, it's going to be 4. 9 times 10 raised to negative 4. Yes. 2.77 times 10 raised to negative 4. Express this number in standard form. Okay. 0, 1, 3, 1, 2, 3, 4. Express in scientific notation. 427,000. 427,000 is 1, 2, 3. It's 1, 2, 3, 5. So 4.27 times 10 raised to 5. 9.647 times 10 raised to 7. 9.647 times 10 raised to 7 power. Okay. Express this number in standard form. Just one decimal place to the left, so we have 0.1488. Okay, cool. Orders of magnitude, multiplying multiples of powers of 10.
I would like to multiply 9 times 10 to the 9th power times negative 2 times 10 to the negative 3rd power. And so I encourage you, pause the video, see if you can work through this. Alright. So the first thing I would want to do is, let's just change the order of multiplication. Let's multiply the 9 and the negative 2 first, and then we can multiply the 10 to the 9th and 10 to the negative 3rd power. So if I were to change the order, we could write this as 9 times negative 2, 9 times negative 2, times 10 to the 9th power, times 10 to the 9th power, times 10 to the negative 3rd power, times 10 to the negative 3rd power. Now what's 9 times negative 2? Well, 9 times 2 is 18, 9 times negative 2 is going to be negative 18. So that's negative 18. And what is 10 to the 9th times 10 to the negative 3? Well, if I have a number raised to some exponent times that same number, 10, has the same base, for both of these,
610 raised to
times that same number raised to another exponent, this is going to be the same thing as that number, as that base, raised to the sum of these exponents. This comes straight out of our exponent properties. So this is going to be 10 to the 9 plus negative 3 power. 9 plus, I should read this close so you see what 9 is negative 3 is. 9 plus negative 3 power. 9 plus 9 plus negative 3 power. Now what's this going to be? Well, this is going to be equal to negative 18 times 10 to the 9 plus negative 3, same thing as 9 minus 3, which is 6. Negative 18 times 10 to the 6th power. And if you wanted to think about what number it is, what's 10 to the 6th? That's 1 with 6 zeros. This is a million. Negative 18 times a million, it's going to be negative 18 million. Or we could say negative 18 times 10 to the 6th. Either way. So this is another way we could have written this.
Negative 18 million.
Negative 18. Negative 18. Maybe write the zeros with the green. Negative 18. Negative 18. Either way is a legitimate way to represent this number. We are asked, what is 10 to the 5th power equivalent to? Well, 10 to the 5th power is the same thing as taking 1. We are asked, what is 10 to the 5th power equivalent to? Well, 10 to the 5th power is the same thing as taking 1 and multiplying it by 10 5 times. So let's do that. So that's 3, 4, and 5. It's 1 times 10 times 10 times 10 times 10 times 10. Notice 1, 2, 3, 4, 5. And what's this going to be? Well, 1 times 10 is 10. 10 times 10 is 100. 100 times 10 is 1,000. 1,000 times 10 is 10,000. 10,000 times 10 is 100,000. So this is going to be 100,000. Now, you might have noticed, every time we multiply this by 10, we're adding another 0 to the product. So if we're multiplying by 10 5 times, we're going to add 5 zeros to the product. So this is literally going to be, it's literally going to be 1, followed by 5 zeros. 1, 2, 3, 4, 5. So 10 to the 5th is the same thing as 100,000. Let's do another one that goes on a similar topic. How many zeros does the product 67 times 10 to the 5th have? Well, there's a bunch of ways of thinking about that. 67 times 10 to the 5th is the exact same thing. This is equivalent to, you could use the 67 times, the last is the same exact logic that we just saw in the previous problem. So 67 times 1 times 10 times 10 times 10 times 10 times 10. And we already figured out exactly what this is. If you have 1 multiplied by 10 5 times, this right over here is going to be 1 followed by 5 zeros. 1, 2, 3, 4, 5. Or it's going to be 100,000. So there's a couple of ways to think about it. If you're looking at just this product right over here, you could say, well, 67 times 1 is just going to be 67. And then every time you multiply by 10, you're going to add another 0. So you could say, well, this is just going to be 67. And we're going to be multiplying by 10 5 times. So we're going to add 5 zeros here. 1, 2, 3, 4, 5. And so this would come to 6,700,000. Another way you can think about it is the same thing as 67 times 100,000. So it's going to be 67. And then we have 5 zeros here, so once again, 1, 2, 3, 4, 5, you get the exact same value. Let's do another one. How many zeros is the quotient 5 what this is? If you have 1 times 10 times 10. We already figured out exactly what this is. If you have 1 multiplied by 10 5 times, this right over here is going to be 1 followed by 5 zeros. 1, 2, 3, 4, 5. Or it's going to be 100,000. So there's a couple of ways to think about it. If you're looking at just this product right over here, you could say, well, 67 times 1 is just going to be 67. And then every time you multiply by 10, you're going to add another 0. So you could say, well, this is going to be 67. And we're going to be multiplying by 10 5 times. So we're going to add 5 zeros here. 1, 2, 3, 4, 5. And so this would come to 6,700,000. Another way. So we're going to add 5 zeros here. And we're going to be multiplying by 10 5 times. So we're going to add 5 zeros here. 1, 2, 3, 4, 5. And so this would come to 6,700,000.
Another way you can think about it is the same thing as 67 times 100,000. So it's going to be 67, and then we have 5 zeros here. So once again, 1, 2. So it's going to be 60. Another way you can think about it is the same thing as 67 times 100,000. So it's going to be 67, and then we have 5 zeros here. So once again, 1, 2, 3, 4, 5. You get the exact same value. Let's do another one. How many zeros does the quotient 5,700,000 divided by 10 to the third power have? Well, 10 to the third power, we already know. 10 to the third power, that's the same thing as 1 times 10 times 10 times 10, which is the same thing as 1,000. And so if we're dividing by that, that's the same thing. So another way of writing this expression right over here. So 5,700,000 divided by 10 to the third is the same thing. As I could write it this way: 5,700,000 divided by 10 times 10 times 10. We could put a 1 out here, which would really change the value, which is equivalent to 5,700,000 divided by 1,000. And either way you think about it, every time you divide by 10, we're going to eliminate one of these zeros. So if you divide by 10 3 times, if you divide by 10 once, you're going to eliminate a 0. Divide by 10 again, you're going to eliminate another 0. Divide by 10 again, you're going to eliminate another 0. You're going to be left with 5,700. Another way of thinking about it is, well, if I'm dividing by something that has 3 zeros, I'm going to eliminate 3 zeros. If I eliminate 3 zeros, I eliminate 3 zeros, I'm left with 5,700. Now, just to be clear, I can only do this if this was 1,000. If this was like 3,000 or something, I could think of this as 3 times 1,000, and then I could only cancel out the 1,000 with these zeros, but the 3 I would then have to divide separately. But only because I'm straight up dividing by 1,000, I'm dividing by a power of 10, I have 3 zeros here, I can cancel out with 3 zeros there. Let's do another one. Or I'll show you a few. And these are the type of exact questions that you might see in the exercise. When 72.1 is multiplied by 10 to the third, the decimal point moves blank places to the blank. And in the exercise, you can see it right. So remember, if you're multiplying by and this is a 10 to the third, you're multiplying by 1,000, you're going to get a larger number. You're not going to get a smaller number. And so every time you multiply by 10, your decimal point is going to move to the right because you're getting larger. So you're going to move the decimal point, so 72.1, if we multiply it by 10 once, then we move the decimal point over 1, so we get 721, which makes sense. 72 times 10 is 720, 72.1 times 10 should be 721. If we want to multiply by 10 3 times, 72.1 times 121, which makes sense. 72 times 10 is 720, 72.1 times 10 should be 721. If we want to multiply by 10 3 times, we're going to move the decimal place over not just once, but twice, and 3 times. And you say, wait, how can I move it over? There's nothing here. Well, you throw a 0 in there. And so you're going to get, it's going to be equal to, so it's going to be equal to 72,100. Now they're not asking us that. They're just asking how we would do it. And we saw the decimal point moves 3 places to the right. And the big key is you're getting a large number when we multiply by 10 3 times, or multiply by 1,000. Let's do this one. When 56 is divided by 10 to the third, the decimal point moves blank places to the blank. Well, divided by 10 to the third is the same thing as divided by 10 3 times. But every time you divide by 10, it's going to become a smaller number. So 56, you might say, where's the decimal point? Well, there's implicitly a decimal point right over there. You divide by 10 once, you're getting a smaller number. 56 is going to become 5 and something. So it's going to become literally 5.6. Divide by 10 again. It's going to become 0.56. Divide by 10 again, like, wait, if I keep moving the decimal place again to the left, what am I moving to the left of? Well, you can throw a 0 right over here. And so if you move the decimal point 3 places to the left, you are left with 0.056. And you might want to put 0 out here just for clarity. But what we did here is we moved the decimal point 3 places to the left in this situation. You got a smaller value.
Yep, that's true. Or just a magnitude exercise.
So we're told Mount Everest is 29,029 feet tall. Estimate Mount Everest's height by rewriting it as a number in the form x times 10 to the y power feet, where x and y are single-digit numbers. So let's think about how we would do this. So x and y could be single-digit numbers. So this is, if we were to write it in scientific notation, we could write something like, let's see, it would be 2.9029, is that right? 2.9029 times 10, I'm actually be careful time is right like that, times 10, I'll use this little caret sign, using shift and 6 to get the caret sign, times 10 to the, and I moved the decimal, let's see, in order to go from 2 to 20,000, I have to add 1, 2, 3, 4 zeros, so times 10 to the 4th. So that's what I would do if they were just asking us to write it in scientific notation. But they're not asking us to write it in scientific notation. They're saying estimate Mount Everest height by writing in this form where x and y are single-digit numbers. So as I wrote it right over here, 2.9029 is not a single-digit number. 4 is a single-digit number, so at least I got the y part right. But I need to write this part, which, you know, in this form, this would be the x. I need to write that as a single-digit number. And the key is they want me to estimate. So if I were to estimate 2.9029, I would write that as 3. So I'm going to go with 3 times 10 to the 4th. If I were to expand out 3 times 10 to the 4th, it would be 30,000 feet. So my estimate seems pretty good. So let's check. There we go. Let's do a few more examples from the orders of magnitude exercise. Earth is approximately 1 times 10 to the 7th meters in diameter. Which of the following could be Earth's diameter? So this is just an approximation. It's an estimate. And they're saying which of these, if I were to estimate it, would be close or would be 1 times 10 to the 7th. And the key here is to realize that 1 times 10 to the 7th, 1 times 10 to the 7th, is the same thing as 1 followed by 7 zeros. 1, 2, 3, 4, 5, 6, 7. Put some commas here so we make it a little bit more readable. Or another way of talking about it is 1 times 10 to the 7th is the same thing as 10 million. So which of these, if we were to really roughly estimate, we would go to 10 million? Well, this right over here is 1.271 million, or 1,271,543. If I were to really roughly estimate it, I might go to 1 million, but I'm not going to go to 10 million, so I'd rule that out. This is 12,715,430. If I were to roughly estimate this, well, yeah, I would go to 10 million. 10 million is if I wanted to really just like one digit to represent it, if I were to write this in scientific notation. This right over here is 1.271543 times 10 to the 7th. Let me write that down. 12,715,430. If I were to write this in scientific notation, it's 1.271,543 times 10 to the 7th. And when you write it this way, you say, hey, well, if I was to really estimate this and get pretty rough with it, and I just rounded this down, I would make this 1 times 10 to the 7th. So this really does look like our best choice. Now let me just verify. Well, this right over here, if I were to write it, I would go 100 million, or 1 times 10 to the 8th. That's way too big. And this, if I were to write it, I'd go to a billion, or 1 times 10 to the 9th. So that's also too big. So once again, this feels like the best answer. Now let's try a couple more. So here we're asked, how many times larger is 7 times 10 to the 5th than 1 times 10 to the 4th? Well, we can just divide to think about that. So 7 times 10 to the 5th divided by 1 times 10 to the 4th. Well, this is the same thing as 7 over 1 times 10 to the 5th over 10 to the 4th, which is just going to be equal to, well, 7 divided by 1 is 7. And 10 to the 5th, that's 10 being, or multiplying 5 tens, and then then you're dividing by 4 tens. So you're going to have 1 10 left over. Or, if you remember your exponent properties, this would be the same thing as 10 to the 5 minus 4 power, or 10 to the first power. So this right over here, all of this business is going to simplify to 10 to the first, or I can actually write it this way. This would be the same thing as 10 to the 5 minus 4, which is equal to 10 to the 1, which is just equal to 10. So this is 7 times 10, which is equal to 70.
So 7 times 10 to the 5th is 70 times larger than 1 times 10 to the 4th. Let's do one more. So here they're asking us 3 times 10 to the 4th. Let's do one more. So here they're asking us 3 times 10 to the 9th is 30,000 times larger than what number? So once again, we can divide. So we have 3 times 10 to the 9th. 3 times 10 to the 9th is 30,000 times larger than what number? So let's just divide by 30,000 and see what we get. And here we've written something in kind of an exponential notation, or we should say scientific notation, actually. And here we just wrote the number out. So one way we could do it is we could either write this number out and then divide, or we could write this in scientific notation. So let's do it either way. So if we were to expand the top number out, if we were to expand this out, we could write that as 3 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll put some commas here to make it readable. And then we're dividing that by 3 followed by 4 zeros. 1, 2, 3, 4. And then we could cancel out the zeros. We could say, okay, let's divide the top and the bottom by 10. Let's divide it by another 10, by another 10, by another 10. And then, let's see, we've done all the dividing by 10. And now let's divide the top and the bottom by 3. So this would become a 1, this would become a 1. So on the bottom, we're just left with a 1. And we'd have 1 followed by 1, 2, 3, 4, 5 zeros. So this would be 1 followed by 1, 2, 3, 4, 5 zeros, or 100,000. Now let's write both of these in scientific notation. So 3 times 10 to the 9th, I'm just going to rewrite that as 3 times 10 to the 9th. And we're dividing that by 30,000, which is the exact same thing as 3 times 10 to the, we have 1, 2, 3, 4 zeros here. 3 times 10 to the 4th. Or I guess I really should say, we have 4 places after the 3. So 1, 2, 3, 4. So 3 times 10 to the 4th. And so we can divide the 3 by the 3, and then that will simplify. So 3 divided by 3 is just 1. And then 10 to the 9th divided by 10 to the 4th, that's going to be 10 to the 9 minus 4, 10 to the 5th. It's going to be 1 times 10 to the 5th, which once again is 1 followed by 5 zeros, or the exact same thing as 100,000. So it's 30,000 times larger than 100,000.
Wait. Still have to do this. Okay, some of them start. Oh shit, this is hard. Okay, so 9 times 10 to the 7th divided by 3 times 10. So 9 divided by 3. 3 times 10 to the 4th power. 3 times 10 to the 4th power. This one. And why am I writing here? Should I do it in here? So 8 divided by 4 is 2 times 4 to the 9th. 2 times 10 to the 9th. Not negative. We have negative 8 over 4 times 10 7 over 10 6 is just 10. Negative 4 to 20. Right? 24. Let's try to evaluate an expression by step by step. Let's try to evaluate an expression step by step. Okay, step 1. Seems incorrect already, step 1. 5 times 10 to the 5th raised to the 5th is how many times it's largest? 1 times 10 to the 5th. 5 times, I guess I don't need to do some kind of select the expression that makes the equation correct. I could say 9 times 6 is negative 18 times 10 raised negative negative 18 raised to 10 Negative 18 times 10 raised to positive 6. Yep. 6 times 10 raised to 8 is how many times as large as 2 raised to 3? Okay, so it's gonna be 3 times 10 raised to 11. Oh fuck. Oh my god, I was doing it. I made the final part. I hate myself so much. 7 answers. Oh my god. I hate myself. I'm dividing. So if I divide, we're adding 10. 3 times 10 to 9. Okay. 2 times 10. Okay, negative 1 minus 10. Oh shit. Come on. 10. Let's see. Negative 1. Okay, try dividing step by step. 1, 2, 3. Okay, cool. 3 times 2 times 10 times 4, negative 3, 6. Oh wow, cool. 4 raised to 10. I mean, if we do this thing, 4, 6. Oh shit, we're deducting that roots 400. Select the expression that makes the equation true. Okay, negative 12 times 10 raised to 9. How many times is large? 3 times 10. Okay, negative 2 divided by 10, negative 8. So if we subtract negative 8 to that, we're gonna have positive 6. Okay, we have 2, 6, 12 times 10. This is just 1. It's 120, bro. Okay, cool. Computing with scientific notation.
Multiply, expressing the product in scientific notation. So let's multiply first, and then let's try to get what we have in scientific notation. Actually, before we do that, let's just even remember what it means to be in scientific notation. So to be in scientific notation, and actually each of these numbers right here are in scientific notation, it's going to be the form a times 10 to some power, where a can be greater than or equal to 1, and is going to be less than 10. So both of these numbers are greater than or equal to 1, and they're less than 10, and they're being multiplied by some power of 10. So let's see how we can multiply this. So this over here, this is just the exact same thing. So I do this in magenta. This is the exact same thing as 9.1 times 10 to the 6 times 3.2
times, actually I don't have to write it, let me write it all with a dot notation to make it a little bit more straightforward. So this is equal to 9 point, do that magenta, is equal to 9.1 times 10 to the 6th times, let me do it in this green color, times 3.2 times 10 to the negative 5th power. Now in multiplication, and this comes from the associative property, essentially allows us to remove these parentheses. It says, look, you can multiply like that first, or you can actually multiply these guys first, you can reassociate them. And the commutative property tells us that we can rearrange this thing right here. What I want to rearrange is I want to multiply the 9.1 times the 3.2 first, and then multiply that times 10 to the 6 times 10 to the negative 5. So I'm just going to rearrange this using the commutative property. So this is the same thing as 9.1 times 3.2 times 3.2, and I'm going to reassociate, so I'm going to do these first, and then that times 10 to the 6th, 10 to the 6th times 10 to the negative 5, times 10 to the negative 5. And the reason why this is useful is that this is really easy to multiply. We have the same base here, base 10, so we can, and we're taking the product, so we can add the exponents. So this part right over here, 10 to the 6 times 10 to the negative 5, that's going to be 10 to the 6th minus 5 power, or essentially just 10 to the first power, which is really just equal to 10. And that's going to be multiplied by 9.1 times 3.2. So let me do that over here. So if I have 9.1 times 3.2, so first I'm going to ignore the decimals. I'm just going to treat it like 91 times 32. So I have 2 times 1 is 2. 2 times 9 is 18. Take a 0 here because I'm in the tens place now, multiplying everything really by 30, not just by 3. That's why my 0 is there. And I multiply 3 times 1 to get 3. And then 3 times 9 is 27. And so it is 2 plus 0, so I'm adding here, 2 plus 0 is 2, 8 plus 3 is 11, carry or regroup that 1, 1 plus 1 is 2 plus carry or regroup that 1, 1 plus 1 is 2, 2 plus 7 is 9, and I have a 2 here. So 91 times 32 is 2,912, but I didn't multiply 91 times 32, I multiplied 9.1 times 3.2. So what I want to do is count the number of digits I have behind the decimal point. I have 1, 2 digits behind the decimal point, and so I'll have to have 2 digits behind the decimal point in the answer. So 1, 2, I'll stick the decimal right over there. So this part right over here comes out to be 29.12. So you might feel like we're done. This kind of looks like scientific notation. I have a number times the power of 10. But remember, this number has to be greater than or equal to 1, which it is, and less than 10. But this number is not less than 10. It's not in scientific notation. So what we can do is let's just write this number in scientific notation, and then we can use the power of 10 part to multiply that by this power of 10. So 29.12, this is the same thing as 2.912. Notice, what did I do to go from there to there? I just moved the decimal to the left. Or another way to think about it, if I wanted to go from here to there, what could I do to this? But I would multiply it by 10. If I multiplied by 10, I would move the decimal to the right. It would go from 2.9 to 29. So if I want to write this value, this is just this times 10. Right? So 29.12 is the same thing as 2.912 times 10. And now this is in scientific notation. That's just this part. And I still have to multiply it by another 10. So times another 10. And so to finish up this problem, we get 2.912 times 10 times 10, or 10 to the first times 10 to the first. Well, what's that? Well, that's going to be this part right over here. That's just 10 squared. So it's 2.912 times 10 to the second power. And we are done.
We are done.
We're asked to multiply 1.45 times 10 to the 8th times 9.2 times 10 to the negative 12 times 3.01 times 10 to the negative 5th and express the product in both decimal and scientific notation. So this is 1.45 times 10 to the 8th power times, and I could just write the parentheses again like this, but I'm just going to write it as another multiplication, times 9.2 times 10 to the negative 12, and then times 3.01 times 10 to the negative 5th. All this meant when I wrote these parentheses times next to each other, I'm just going to multiply this expression times this expression times this expression. And since everything is involved in multiplication, it actually doesn't matter what order I multiply in. And so with that in mind, I can swap the order here. This is going to be the same thing as 1.45, that's that right there, times 9.2, times 9.2, times 3.01, times 3.01, times 10 to the 8th, let me do that in that color, times 10 to the 8th, so times 10 to the 8th, times 10 to the negative 12th power, 10 to the negative 12th power, times 10 to the negative 5th power, times 10 to the negative 5th power. And this is useful because now I have all of my powers of 10 right over here. I could put parentheses around that. And I have all of my non-powers of 10 right over there. And so I can simplify it. If I have the same base 10 right over here, so I can add the exponents. This is going to be 10 to the 8 minus 12 minus 5 power. Minus 5 power. And then all of this on the left-hand side, let me get a calculator out. I have 1.45, you could do it by hand, this is a little bit faster, it's likely to make a careless mistake, times 9.2 times 3.01, which is equal to 40.1534. So this is equal to 40.1534, and of course this is going to be multiplied times 10 to this thing. And if you simplify this exponent, you get 40.1534 times 10 to the 8 minus 12 is negative 4, minus 5 is negative 9. 10 to the negative 9 power. Now, you might be tempted to say that this is already in scientific notation, because it has some number here times some power of 10, but this is not quite official scientific notation. And that's because in order for it to be in scientific notation, this number right over here has to be greater than or equal to 1 and less than 10. And this is obviously not less than 10. Essentially, for it to be in scientific notation, you want a non-zero digit right over here, and then you want your decimal, and then the rest of everything else. So here, and you want a non-zero single digit over here. Here we obviously have, here we have 2 digits. This is larger than 10, or this is greater than or equal to 10. You want this thing to be less than 10 and greater than or equal to 1. So the best way to do that is to write this thing right over here in scientific notation. This is the same thing as 4.01534 times 10. And one way to think about it is, to go from 40 to 4, you have to move this decimal over to the left. Moving a decimal over to the left, to go from 40 to 40, you're dividing by 10, so you have to multiply by 10 so it all equals out. Divide by 10 and then multiply by 10. Or another way to write it, or another way to think about it, is 4.0 and all this stuff times 10 is going to be 40.1534. And so you're going to have 4, all of this times 10 to the first power, that's the same thing as 10, times this thing, times 10 to the negative 9 power. And then once again, powers of 10, so 10 to the first times 10 to the negative 9 is going to be 10 to the negative 8 power. 10 to the negative 8 power, and we still have this 4.01534 times 10 to the negative 8. And now we have written it in scientific. Now we have written it in scientific notation. Now they want us to express it in both the decimal and the scientific notation. They're asking us to write it in decimal notation. They essentially want us to multiply this out, expand this out. And so the way to think about it, write these digits out. So I have 4, 0, 1, 5, 3, 4. And if I'm just looking at this number, I start with the decimal right over here. Now every time I divide by 10, or if I multiply by 10 to the negative 1, I'm moving this over to the left one spot. So 10 to the negative 1, if I multiply by 10 to the negative 1, that's the same thing as dividing by 10, and so I'm moving the decimal over to the left one. Here, I'm multiplying by 10 to the negative 8, or you can say I'm dividing by 10 to the 8th power. So I'm going to want to move the decimal to the left 8 times. So move the decimal to left 8 times. And one way to remember it, look, this is a very, 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 very small number. If I multiply this, I should get a smaller number, so I should be moving the decimal to the left. If this was a positive 8, then this would be a very large number. And so if I multiply by a large power of 10, I'm going to be moving the decimal to the right. So this whole thing should evaluate to being smaller than 4.01534. So I move the decimal 8 times to the left, 8 times to the left. I move it 1 time to the left to get it right over here, and then the next 7 times I'm just going to add zeros. So 1, 2, 3, 4, 5, 6, 7 zeros. I'm going to put a 0 in front of the decimal just to clarify it. So now I know this, if you include this digit right over here, I have a total of 8 digits. I have 7 zeros, and this digit gives us 8. So then 1, 2, 3, 4, 5, 6, 7, 8. The best way to think about it is I start with the decimal right here. I move once, twice, 3, 4, 5, 6, 7, 8 times. That's what multiplying times 10 to the negative 8 did for us. And I get this number right over here. And when you see a number like this, you start to appreciate why we write things in scientific notation. This is much easier to take up space to write, and you immediately know roughly how big this number is. This is much harder to write. You might even forget a 0 when you write it, or you might add a 0. And now the person has to sit and count the zeros to figure out essentially how large, or get a rough sense of how large this thing is. It's 1, 2, 3, 4, 5, 6, 7 zeros, and you have this digit right here. That's what gets us to that 8. But this is a much more complicated looking number than the one in scientific notation. We have 7 times 10 to the 5th over 2 times 10 to the negative 2 times 2.5 times 10 to the 9th. So let's try to simplify this a little bit. And I'll start off by trying to simplify this denominator here. So the numerator is just 7 times 10 to the 5th. And the denominator, I just have a bunch of numbers that are being multiplied times each other. So I can do it in any order. So I'm going to swap the order. So I'm going to do it 2 over 2 times 2.5 times 10 to the negative 2 times 10 to the negative 2 times 10 to the 9th times 10 to the 9th. And this is going to be equal to, so the numerator I haven't changed yet, 7 times 10 to the 5th over, in the denominator, 2 times, let me do this in a new color now, 2 times 2.5 is 5, and then 10 to the negative 2 times 10 to the 9th. When you multiply two numbers that are being raised to exponents, and they have the exact same base, it's 10 to the negative 2 times 10 to the negative 9, we can add the exponents. So this is going to be 10 to the 9 minus 2, or 10 to the 7th. So times 10 to the 7th. And now we can view this as being equal to, this is being equal to 7 over 5, 7 over 5, times 10 to the 5th over 10 to the 7th, times 10 to the 5th, 10 to the 5th over 10 to the 7th, 10 to the 7th, do it in the orange color to keep track of the colors, 10 to the 7th. Now what is 7 divided by 5? 7 divided by 5 is equal to, let's see, it's 1 2/5 or 1.4.
Wow.
This right is 1.4. And then 10 to the 5th divided by 10 to the 7th. So that's going to be the same thing as, and there's two ways to view this. You could view this as 10 to the 5th times 10 to the negative 7. You add the exponents, you get 10 to the negative 2. Or you say, hey, look, I'm dividing this by this. We have the same base. We can subtract exponents. So it's going to be 10 to the 5 minus 7, which is 10 to the negative 2. So this part right over here is going to simplify to times 10 to the negative 2. Now, are we done? Have we written what we have here in scientific notation? It looks like we have. This value right over here is greater than or equal to 1, but it is less than, or it's less than or equal to 9. It's a digit between 1 and 9, including 1 and 9. And we have, and it's being multiplied by 10 to some power. So this is, it looks like we're done. This simplified to 1.4 times 10 to the negative 2. Equal to 1, and it's being multiplied by 10 to some boxes. It looks like we're done. This simplified to 1.4, or it's less than or equal to 9. Value right over here is greater than or equal to 1, but it is less than, or it's less than or equal to 9. It's a digit between 1 and 9, including 1 and 9. And we have,
No, you have
and it's being
9.5, bro.
Yeah.
That's wrong.
We have 7 multiplied to 1 times 10 to the negative 2. This is, it looks like we're done. This simplifies to 9. And equal to 9. It's a digit between 1 and 9, including 1 and 9. And
Actually going to report the mistake. It's
equal to 9. It's a digit between 1 and 9, including 1.
35, right? a is less than or equal. Yo, how do I post this? Yo, what the fuck? I can't even post. Okay, cool. Calculate the quotient below and give your answer in scientific name. Need a calculator. Okay, cool. So let's you might. So it's gonna be 10 to the third power. Let's see. It's still 7.8. The third power. So this just be the same, right? Going to be 15 times 10 to the 4th. 4. No way. I made a mistake. No way. Oh shit. Of course. Okay. Let's see. -5 minus -4 is going to be just -1, right? Then raised to -1. Yeah, there's 4.16 times 8, 33.8, that should be 3.338. So from where it moved. Zero? What? I mean, -5 minus -4 is going to be -1, right? The 4.16 times 8 is 33.28. 8 times 10, -1. 10 raised to -1, right? So am I supposed to say 10? -2? What the fuck? Scientific notation. The 33. Yo, what the fuck? This is 33.28 times 10 raised to -1. It should be -1, right? The fuck? Then we're going to essentially multiply this by 10 to -1. to move this guy over there. And then we're adjusting pi. This thing with -2, but apparently it's incorrect. 0, 1, +2 is 10. What the fuck? Maybe I'm wrong with this part now. Did I just multiply it? Fuck. Oh. Okay, so oh my god, so 0.52 times 10 raised to -1. So I kind of moved that over here. So if I move then this is correct. What's this? 1, 2, 3, minus 4. Then raised to 4, and then 7. Kasi oh my god. Now this is interesting. Okay. So you have 1.2 divided by 6, right? So 0.2 times 10 raised to 1. Then if we're multiplying this by 10, so we have 2, and then we're going to just spell 0. So 2. Then raised to 8. We have to divide by 1, so we then raised to 9. 8. Yeah. Start quiz. Let's go. Should I do the question separate? Go. No. Is it fair to say you have to divide it by 2.94 times times 10 based on what number? This is 3, then we have 10 raised to 3. 10 raised to 3. Then if we have 0.94, and then we multiply that by 10, 9.4 then. Oh man, I'm confused. If we multiply it by 10, we're going to divide this one. This is right. Oh shit, I don't know. I mean, if we turn it... It's 940, what the fuck? Ah yeah, of course, then if we make it scientific, then we have 9 times 4 times 10 raised to 1. Oh my god. It's raised to 1. Yo, this is insane. This is 94 though. 1.8 times 10 to the 6 divided by 2, how can is equal to 40? But this one only gives us 94, so we can pick 10. The problem is $7,000. Holy shit. Tens, 100,000s. 3,763,000. It's gonna be 763,000. I don't know what's the answer. So we have 7.63 times 10 raised to -1. Wait, what? No. If this is the guy, then just move one time. Then oh man, I'm getting confused a bit. Say it's thousands, then multiply by 10, and then how many is 1, right? So 1 times 10 1. Oh my god. I don't know how I feel about this. Santiago tried to evaluate expression. Find Santiago's mistake. Let's find his mistake. A bit dramatic, but okay. So this is 1, 1, 1, 2, 3, 4. Okay, 4 times 10, 3 times 5, 4 times 3, 10 times 5, 12 times 10. Oh, no. It's a mistake. Okay. 3.643 times 10 raised 1. 364 Oh my god, this is gonna be 1 times 5, 10, 4, 6, 10, 2, second power, or 100. Okay, let's see. 10 to the second power, right? 6 minus 4, 2, 1, 200. Okay. Ugh. We're gonna do this unit test in a separate vid. That's it for now. 8% mastery here. 9, cool. See stuff. Okay, consistency go, listener. Okay. Oh, 77% of world math. Okay. That's it for this part. Bye.